Welcome to qnawire.
We have another kind of crazy uh, reheat regenerative um, uh, with feedwater heater system here. This mess here. So we'll kind of let me go through the system. It's illustrated in the book. So, but you have stuff going through the boiler into the high pressure turbine, come out of the high pressure turbine being reheated in the boiler, going to low pressure turbine. Then we have two bleed lines, one going to the higher pressure one going to an closed feed water heater, the lower pressure one going to an open feed water heater, and then the outlet going to the condenser. Now the first pump pumps the pressure back up so that it is the same as at 12, and then it mixes with stuff coming out of that went through the closed feed water heater and had its pressure dropped, so that 7 2, 7, and 12 all have the same pressure, and then likewise 3 has the same pressure. And so everything is mixing in here. And then we get pump 2 pumps everything back up to the boiler pressure. So the boiler pressure is 15 megapascals. Um, Coming out of the high pressure turbine is 1 megapascal, which is what's going into the low pressure turbine. The first bleed is at 600 kilopascals, the second is at 200 kilopascals, and then the condenser operates at 5 kilopascals. Um, we have a fraction of Y coming off at the first bleed and a fraction Z coming off at the second. Let's see here. So again, our TS diagram is kind of a mess, but again, we can see, all of these states, the reheat here, the bleed, um, the feed water heater, let's see here, this would be the from 6 to 7. This is from the expansion valve. Go get it from this pressure down to this pressure, and then 7, 2, and 12. So 7, 2, and 12 all meet up together to go into um, come out at 3, and a bit pumped up, and then to the boiler again, and so that is our cycle. So let's see here. We want to analyze. We can look at the pump, this low pressure pump. So we get a enthalpy, specific volume. We know the pressure change, so we can get the power, the specific work into the pump here. And that means we can get the enthalpy coming out of the pump, specific enthalpy that is. Now at 3 here, we're told we have a saturated liquid that is at 200 kilopascals. So we get the specific enthalpy, specific volume there. And likewise, we know the pressure change across this pump, so we can get the specific work being put into this pump, and also the specific enthalpy coming out. Now, across this expansion valve, we have constant enthalpy, okay, assuming there's no heat transfer there, and obviously no mechanical work being done or electrical work. So then we have those two things are equal, and we know that 6 is a saturated liquid. So 7, we expand it to a higher pressure, lower pressure, so we wind up with a two-phase. We get basically some boiling in here because of the pressure drop. And then we go into here. And so we can also get the specific volume at 6 because we know the saturated liquid and we know the pressure. Now, why we need that is if we take a look at this feed water heater here. Now, we're going to assume that the temperature coming out here is the same as the temperature coming out there, so that we basically have perfect heat exchange here. Now, the the enthalpy, so we have, let's see here, we have this is all saturated liquid. To be just basically, this is all or saturated or subcritical liquid. So that's one thing to note. Everything through here is basically well, not coming in here, but anyway. So we can look at this system here where we have what's coming out here, right? And then it's going through here, and then there's pressure dropped and then is increased, right? So we have a difference in pressure here, but the specific volume is basically the same. So what happens is in this loop here, basically from here to here, we have an incompressible fluid. So, and again, we can get that specific volume. So the enthalpy here is the enthalpy here plus the work that was done in getting the pressure, the difference in the pressure. So that gives us the enthalpy at 5 going into the boiler. All right. So let's see here. We have, so I mean, basically we're doing a control volume kind of, I don't even know how to draw it. Cut here, and then everything kind of out here. Is that what we're doing? Is that what I'm thinking? No. Yeah. Yeah, it's basically just a weird control volume. We're just looking at the flow through here. Pressure, there's a pressure difference in here. Specific volume is the same. And so we're basically just looking at, how this stuff coming out here gets back up to here. So it has some enthalpy here, and then we put some mechanical work into it because the pressure difference is here. We get some, I mean, we lose some pressure here, but we gain some pressure here. So the thing is that it's a saturated liquid here. It's also pretty much a saturated liquid here at the same temperature, roughly. So it is, let's see here. We have, it's not a saturated liquid here, obviously. But once it mixes here, it is. And then, so we have just we put some work in, we take some out, put some in. And so the net between here and here is the difference in the, and the pressure at 4 is the same as the pressure at 5. So that's kind of, this one here is the same as 4. So that's what this equation came from, basically looking at the fluid that's coming out of here and then coming back in this loop. So it's a little weird, but I hope I explained that okay. Again, coming, let's see here. Yeah, it's so we have Y coming through here, Y coming into here. Here we have total. Yeah, but essentially we're increasing the enthalpy by adding pressure to what came out here. You can almost think of it as kind of a little internal pump that went from here to here, kind of bypassing that. It's kind of weird. It's all the fact is that it's all saturated liquid in here, and so that's why you can kind of get away with this kind of stuff. So anyway, I'm not sure exactly how else to proceed on this. I don't think we have enough information other than to kind of do this business here. Anyway, we know the pressure and temperature out of the boiler. So that one's easy. Enthalpy and entropy. We know let's see here, we know it's isentropic, and we know the pressure, so we can get the enthalpy at 9. And then the enthalpy at 10, we can get because we know the pressure and temperature again. So we get the entropy there. And then at 11, because it's isentropic, and we know the pressure, we can get the enthalpy again. So what we can do then is, let's see here. One of the things to note, really, is that you can look at the difference in these two, coming back to this mess here. You can look at the difference in these two things, and there's not much, right? It's gonna, if we would have just said H5 was H6, it probably wouldn't have changed the numbers all that much at all, just because, again, the work in getting the pressure up is very small compared to what is done, what's put into the boiler, and then what we get out of the turbines. Anyway, so now let's see, where are we at? We need to go to 12. So 12, we have entropy is the same as at 10, and we have pressure, so we can get enthalpy. Then at 13, likewise, entropy is the same as at 10, and we have pressure, and we find that we're two-phase, so we can get the quality factor and the enthalpy. Now, this here, 6 and that is an energy balance on, let's see here, 5 and 6, or 11 and 6, and that's an energy balance on this feedwater heater, right? So we're looking at the changes in here. And that's where we kind of got messed up. Like we needed to have H6, or we needed to have H5 here, because we needed to have this. If we did an energy balance on here, we didn't know what H5 was. We could have, again, kind of assumed that it was the same as H6. And that would have, done some things here. But anyway, we can, again, it's, again, looking at 5. So 5, I didn't really draw this right, but 5 and 6 are at the same temperature. And so, we went from a pressure here to a pressure there. You can kind of look at it that way, but in a circuitous route, okay? Because we went through here, here, and then up to here, 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 up to here. But really, in going from here to here, we changed the pressure, basically. And specific volume didn't change much. So we needed to change the enthalpy by a little bit. So we got a little bump in enthalpy there. Now, let's see here. Where are we now? So now we can do this energy balance. And that will give us this ratio of M11 to M.5, which is Y, right? So this ratio is Y, the percentage of flow we're extracting at the first bleed, right? And so we can just solve for Y here, or get that ratio, and we wind up with that winds up being about 6.3%. And now we can do an energy balance on the open feedwater heater here. And let's see here, we have all these flows in. So we have, the enthalpy, the energy flow in, the energy flow out. And then dividing through by M11, or M5, sorry, M5, right, is the same as M3. So essentially we're dividing through by M3. And so this M12 over M5, M.12 over M.5 is Z. M.2 over M.5 with conservation of mass is 1 minus Y minus Z. And M.7 over M.5 is Y again, because 7, let's see here, 7 and 11 are the same. The flow through here is the same. Okay, so some conservation of mass stuff involved with this too. But what this gives us is an equation where the only thing we don't know is z. And so that's the fraction of flow we bled off at the first bleed, and that's 11.65%. Oh, no, the second bleed. Sorry, the second bleed, 11.65% we took off there. Okay, so that gives us enough information to figure out heat transfers. So the specific heat going into the boiler, okay, and that one's just, you know, the enthalpy differences here and here and here and here. That one's easy because we have the same flow going through here and through here. So we just need to look at the enthalpy differences. So that gives us that. And then out, we got to remember, just look at the enthalpy differences across the condenser, but we got to remember that the mass flow rate through here is not the mass flow rate through here. To normalize it on the same basis, we need to take it. The ratio is 1 minus y minus z. So 1 minus y minus z is the fraction of the flow going through here. So that is our factor here, and then the change in enthalpy. So we get the specific heat transfer out. The difference in those two is the net work, specific net work we get out. Then we can get the efficiency, the thermal efficiency, by taking this divided by this, or 1 minus this divided by that, either way. And that winds up being 48.5%. And then we can figure out the actual power out of the net power out of this, because we know the mass flow rate. I think somewhere we were told the mass flow rate. I thought somewhere. Did I not write that down? Oh, let's see here. The net flow rate of 42. So m dot about 5. Or just call it 5. Same as 8, same as 4, same as 3, same as 9, same as 10, is 42 kilograms per second. So we take 42 kilograms per second, multiply it by our specific work, and we get a net power, our net power out of this plant of 72.4 megawatts.